Okay, so this starts our unit about equilibrium. These are IB topics 7 and 17. Okay, so we've got ourselves a glass of water. Well, typically, if we just let it sit, we'll see that water level go down as evaporation occurs. Okay, and depending on the temperature, we get different rates of evaporation, but one way or another, it'll evaporate. Okay, and what happens if we put a lid on it? Well, that evaporation is actually still going to occur, but so will condensation. If you've ever, drunk a bottle of water about halfway, put the lid back on it, you start to see those little beads of condensation. And so you've got here equal rates of evaporation and condensation. And that is equilibrium, when the rates equalize, okay, when the rates are equal. Okay, so chemical equilibrium deals with chemical processes and with physical processes that are reversible. Okay, so we have water going from a liquid to a gas, there's your evaporation, and we have it going from gas to a liquid, so condensation. Okay. So the way we write this is with this nice little double arrow. That's our equilibrium symbol. Okay, so this is almost like going up a down escalator, if you think about it. If you're walking up and the stairs are moving down, but you're staying in place, like almost as if you're on a stair climber or a treadmill or something, then you are at equilibrium because you're not really moving anywhere. All right, let's take a look at this example. We have nitrogen, hydrogen reacting to form ammonia, and plus 22 kilocalories, so this is exothermic. Okay, so we have our forward reaction. We also have the reverse reaction, and so that's reversible. Now, reversible reactions, what we're dealing with here are ones that don't go to completion. So we can have these occur in either direction. And I want to clarify right now, we are not talking about the speed of the reaction. We're talking about how much reactant or product is formed or remains. Okay. So chemical equilibrium exists when the forward and the reverse reactions occur at exactly the same rate. And hence, the concentrations of those reactants and products remain constant. So draw this in. I want you to write yourself a little note. Notice that here on this first one, we start out with just hydrogen and iodine, and we start out with 0 HI. But on this other one, we start out with 0 hydrogen and iodine, but we have a good bit of HI. Notice that the positions of equilibrium, where those lines flatten out and stay constant, is the same. Okay. So we'll talk more about this, but equilibrium can be reached from any given position. Okay. So at equilibrium, if there are more products than reactants, we say that this is product favored, or we could say that equilibrium lies to the right, because when you write an equation, the products are on the right. If there's more reactants than products, we say that it's reactant favored, or that the equilibrium lies to the left. I would recommend actually using the words reactant and product favored over left and right, because sometimes people get those twisted around, but products and reactants seem to stay more consistently correct. Okay, so let's talk about some characteristics of the equilibrium state. The first one is that equilibrium is what we call dynamic. So the reaction hasn't stopped. The forward and backwards reactions are still occurring. They're just happening at the same rate. Okay? And at equilibrium, it also has to be achieved in a closed system. So like putting a lid on that cup of water, putting the lid on your water bottle, putting a stopper in your flask. And this prevents the exchange of matter with the surroundings, so it forces those reactants and products to react and recombine with each other rather than escaping and reacting with something else. Okay, the concentrations of the reactants and the products remain constant because they're being produced and consumed or destroyed at equal rates. And when we reach equilibrium, this is the silly thing, it looks like the reaction has stopped. It hasn't, but it looks like it because there's no change in those macroscopic properties, things like color and density. Because once the concentrations of the components are constant, then that color is going to stay constant. The density would stay constant. So although things are still happening at a molecular level or a particle level, we don't see those. We just see the big picture and it looks consistent. Also, equilibrium can be reached from either direction. Okay, so the same equilibrium mixture will result no matter we started with all reactants, all products, or a mixture of both. Okay, so here's just a couple reminders, some big takeaway points. Okay, so equilibrium, our dotted line starts where those lines flatten out, so where our concentrations remain constant. And those macroscopic properties also become constant. Okay, and it does not mean that the reactants equal the products. It means that the concentrations are constant. And so we can have reactants equals products, but that's not going to happen a whole lot. And lastly, the composition of the reaction mixture at equilibrium is independent of the starting concentrations. So again, it doesn't matter if we start with all reactant, all product, a mixture, we're going to get it taken care of. All right, so let's look at some practice ones. These are your checks for understanding. Let's say we have physical equilibrium. So we've got ice sitting in water and it's all at 0 degrees Celsius. So 0 degrees Celsius is the freezing point for water and it's the melting point for ice. And so we can have an equilibrium here. Okay, we don't get to see this a whole lot because we don't really get this cold around here, but it could happen. So at any given point we have ice molecules leaving and going to the liquid phase, and we have liquid water going and attaching to that ice molecule or that block of ice and becoming an ice molecule in a static phase. All right. So here's a question to go with it. Which statement or statements is or are true for a mixture of water and ice at equilibrium? So take a minute, think about that, try and answer it. All right, so Roman numeral 1, the rates of melting and freezing are equal. Yes, because it's the rate. And that's what makes something at equilibrium, when the rates are equal. So yes for Roman numeral 1. 2, the amounts of ice and water are equal. No, we don't have to have that. It could happen, but it's not necessarily going to. Okay, the same position of equilibrium could be reached by cooling water and heating ice. Yes, because we can reach it from either direction. So 1 and 3, letter B. Okay. So we could also have something, say, at the boiling point due to evaporation, where we have evaporation condensation happening. So let's take a look at this question along the similar lines. Which statement is correct for the equilibrium of liquid water to gaseous water in a closed system at 100 degrees Celsius? So think about it for a sec and then we'll talk. All right, so all of the liquid water molecules have been converted to gas. Well, no, because it's equilibrium. We've got 2 arrows. It's going back and forth. The rate of the forward reaction is greater than the reverse reaction. Well, we just said we're at equilibrium, so that means the rates are equal. So not for B. The rate of the forward reaction is less than the rate of the reverse reaction. That one's incorrect too. The pressure remains constant. Okay. You wouldn't really think about this, but the pressure would remain constant because the concentration of water vapor is constant, and that's what would be exerting pressure. So D is correct. Okay, we could also think about equilibrium, physical equilibrium, in the context of some sort of compound. It's maybe only slightly soluble in water, or it's a saturated solution, and so we've got our crystal of whatever, and we see that some molecules are going into solution and some molecules are reattaching to the crystal. Okay, so if we had like a saturated solution, this would be an example. We have salt, this is all sorts of salt water, and then we've got extra salt on the bottom, but it's not just sitting there statically. There's some ions that are leaving the crystal and some that are reattaching to the crystal. So here's our third check for understanding. Which statement is correct for a crystal of iron 2 sulfate in a state of equilibrium with a saturated solution of iron 2 sulfate? Okay, so the color of the solution darkens as the crystal continues to dissolve. No, it's at equilibrium, it's saturated, so we're not going to have the whole thing dissolve. Okay, the concentration of the iron 2 sulfate increases as the water evaporates. It can't evaporate, we have a stopper. The shape of the iron 2 crystal, or iron 2 sulfate crystal does not change. Well, we can't guarantee that because we've got particles that are leaving it and reattaching. D, the color of the solution does not change, but the shape of the crystal may change. Okay, the color of the solution shouldn't change because the concentration should stay constant. So the first part of that is correct. The shape of the crystal may change. That's correct as well because we have those ions that are going into solution and coming out of solution. And so the shape of the crystal could change. It doesn't have to, but it could. So D would be your correct answer. And there's your intro to